Good morning, good day, and good evening to all our attendees joining us for today's latest Data Science Central webinar. I'd like to start our event off today by thanking Tableau for sponsoring today's webinar. Tableau is a wonderful supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Cisco, Teradata, TIBCO, Hortonworks, Pivotal, and Oracle, to name just a few. These webinars are available on demand at datasciencecentral.com, and if you've not had the opportunity to view them, I would encourage you to take a look as they do provide some very useful information. Today's webinar is entitled The Beautiful Science of Data Visualization. And before we begin, I'd like to just briefly review the format of today's webinar. Today's event will be approximately 1 hour long. We have a single panelist that I'll introduce to all of you in just a few moments. We should have about 10 to 15 minutes for Q&A following this presentation, and the event is being taped and will be made available later on this afternoon at datasciencecentral.com. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing them and presenting them on your behalf during the Q&A portion of today's webinar. My name is Tim Matteson. I'm one of the co-founders of Data Science Central, and I'll be your host for today's event. I'm very pleased to introduce today's speaker, Jeff Pettiross of Tableau Software. Jeff is the User Experience Manager at Tableau. He has been dreaming about information design and user experience since he was a kid, spending hours sketching out interface elements for games he would write on his TRS-80. Since then, he has spent the last 25 years designing software and information visualizations in diverse fields, including data analysis and visualization, healthcare, project management, desktop software, and engineering. As User Experience Manager, he races to keep up with the great ideas about flow generated by the rest of Tableau. Thanks for being with us, Jeff. We're looking forward to your presentation. Seeing and understanding data is richer than creating a collection of queries, dashboards, and workbooks. We'll see how visual and cognitive science explain what makes data visualization so deeply satisfying. Why does a collection of bars, lines, colors, and boxes become surprisingly powerful and meaningful? How does fluid interaction with data views multiply our intelligence? 3 decades of research into the beautiful science of data visualization explain why history have converged at this moment and why interactive data visualization has brought us to the verge of an exciting new revolution. So Jeff, I'm going to pass it over to you. You can begin as soon as you're ready to go.
Great, thanks Tim. Hello everyone. I would like to talk about data visualization today. I think it is one of the most significant technologies of the 21st century. And I'm not trying to be hyperbolic about some software, Tableau or otherwise. I'm not even really talking about computer code. Those of us who take the plunge and put our data visually are not simply reimagining business intelligence for a new era. What we are doing together is introducing our companies, our colleagues, and our friends to a fundamentally new way to apply the best science about perception and cognition to the ever-expanding ocean of personal and business data. With our combined creativity, we're pioneering an entirely new field of inquiry. My goal is that you will leave this webinar today with a deeper understanding of a beautiful technology you probably already use every day, the science of seeing and understanding data. So my name is Jeff Pettiross. I've been here at Tableau almost 4 years now. My background is in computer science, software design, and data viz, like Tim mentioned. And now I lead a team of 15 user experience designers here at Tableau. I get to work alongside people with doctorate degrees in computer science. These are people who are inventing new algorithms and new technologies for databases and ways to arrange data on the screen. I get to work with user researchers who teach me how people actually interact with computers. But one person of note I want to call out is my manager. He's a man named Dr. Jock McKinley. He actually helped invent the field of computerized information visualization 30 years ago when he was working at Xerox PARC, their Palo Alto Research Center. But data viz, of course, stretches back much further than just 30 years. So I'd like to take us through an example from almost 150 years ago. In 1869, Charles Minard created this data visualization. It's now one of the most famous examples cited by viz experts. On just one sheet of paper, It explains the beginning of the end for the French Empire and its leader, Napoleon. Let me add a little context. So in 1801, France looked about like this, which is what it looks like today. In 1804, Napoleon Bonaparte became the Emperor of the French and started a decade-long campaign of expansion. By 1812, thanks to an aggressive military campaign, the French Empire looked much more like this. Here, at the height of his power, Napoleon wanted to score a decisive victory over Russia by taking his army to Moscow. This turned out, though, to be a profound mistake, and much of the reason why France still looks like this today. So, let's go back to the viz. In June of 1812, Napoleon assembled his massive army in Poland and headed east toward Moscow. That's shown by the thick orange line. Over the next several months, brutal and efficient Russian tactics deprived the French a supply line, and the French numbers steadily dwindled. These losses are reflected in the orange line. It gets thinner and thinner as they march from left to right, west to east. When the French finally reached Moscow, over at the right edge of the drawing, Napoleon found no army there to fight. The Russians had abandoned and burned their own capital. Napoleon had no one he could force to surrender, and he still did not have the decisive win that he needed. By now, it was September, though, and the harsh Russian winter was setting in. Napoleon was forced to turn back, but the return trip, the heavy black line from Moscow back to Poland, was doubly cursed. In addition to ongoing Russian attacks, there was the deadly cold. That temperature line graph along the bottom reads from right to left, from east to west, mapping temperatures to location. You can see the temperature reaches a low of minus 37 degrees Celsius in Malozhetchna. The black line shows a staggering loss of life, growing thinner as it goes from east to west. Nearly all the French soldiers were killed, and Napoleon did not deliver any major victory. This effectively ended his campaign of expansion and started the decline of the French Empire. And this entire story is captured in this early masterwork of data viz. Minard skillfully combines position, color, line width, and thoughtful labeling in one view to tell a story of troop strength, distance, temperature, location, and ultimately a tale of hubris. So Jacques Minard had this intuitive sense of how to communicate data visually. His intuition made him a pioneer of a new field of inquiry, one that would eventually become the beautiful science of data visualization. So why do I call it a science? Well, this field is backed by or built on the proven observations of cognitive and perceptual psychology. In other words, scientists have actually studied how our brains perceive and think, and that gives us concrete ways we can help people see and understand data. So how do we as humans actually do this? Let's take a look at the brain. We all have brains, and they're not some undifferentiated mass of goo. While our understanding of this organ is still rather primitive, we do know that there are many different parts of the brain. For example, the prefrontal cortex is an area critical to planning and personality and decision-making. It's right at the front of your brain. Together now, let's go on a tour of our brains by exploring some of its parts and using them a little. Well, how many circles are there? Probably counted pretty quickly, up to 9. Why am I starting here? Well, there's a part of your brain that just lit up when I asked you to count. This is a very specific part of your brain. It's different from the part that knows a lot and a little. There's actually even a different part that's responsible for numerosity, counting up to 5. This part of your brain that lit up is made just for counting numbers. Now that we got your counting centers all warmed up, let's count some more. How many 9s do you see? Well, it's hard to see them in this case because you have to scan all the numbers one at a time and find the ones that you're looking for. But we can make it a lot easier. Now how many 9s do you see? When they're colored red, they pop right out. It's actually called perceptual pop-out. The red activates a different part of your brain, the visual cortex. It's good at discerning color hues. A wonderful thing about our brains now is that there are lots of these parts all working together. Sorting by color and counting work together in tandem. We didn't have to learn how to do that. Of course, we can take advantage of this in DataViz too. Let's look at some numbers with a little bit more meaning. So each number here represents one country. Specifically, it's the percent of that country's economy they spend on the military. So, for example, this 5 here means that the United States spends about 5% of its GDP on the military. So what if I want to know how common it is to spend 5% or more in the military across these countries? I could look for all the numbers 5 or bigger, or, again, I could just color them and take advantage of visual pop-out. Now it's quick to see 3 yellow countries in Europe and the Americas that spend more than 1/20 of their GDP on military. Again, we used color perception and numerosity in this case. Now, if I take it a step further and sort these values, we start to see groups of similar values. We build on our intuitive sense of relationship and proportion. If I add another part of the world, the Middle East, again, color perception helps us draw some conclusions before we even really understand what we're seeing. But now, instead of precise counting, we draw on a rough estimation of size and proportion that's informed by color. We layer this visual intuition on top of our cognitive understanding of the world and come to new conclusions. We could also look at this information on a map. Now we've traded the positional information of sorting and used the position to communicate geography. We still get the fast visual grouping of the yellow countries all together, which is informed by the slower cognitive process of understanding geography. By the way, if you're wondering where the 2 yellow European countries went, they are still there, but they're just too small to show at this scale. You may also notice that we're getting into sort of a dialogue with the data. We see something, we develop an understanding, and we ask a new question. So let's ask another one. These images are all about percent, but what about absolute spending on the military? We can add total spending as a new kind of visual cue, size, and a new understanding of the data comes to light. Now we can see which countries not just spend the most of their money, but which ones also spend the most overall. So one section after another, we lit up different parts of our brain. We assign meaning to things like position, color, and size. And we did it quickly, forming ideas rapidly with each image. But there's a downside to all that power to quickly create meaning. Our own brains sometimes betray us and give us the wrong meaning. When I was a kid, I remember when they invented ATMs, cash machines. This is a relatively modern ATM here with a color screen instead of the 2-line LED red readout that I remember on some original models. When ATMs came out, my mother worked for a bank. The bank itself was unremarkable except for one thing. They had the vision to foresee that ATMs would become popular. It was not a given at the time. You may remember that people would trust machines to accurately replace human tellers. But this little bank, it was called Connecticut Bank and Trust, believed in the power and convenience of ATMs. And they saw it as their mission to build trust in these new machines. So they literally put a friendly face on them. Meet Barney. This name and this face were the brand of these ATMs. The designers of this logo knew how to create meaning for human beings. 3 circles, 2 curves, 2 triangles, and a line, and we see a face. And not just any face, but one that suggests trust. Now, the Barney brand was incredibly successful. It was so recognizable in the region that any bank's ATM became known as a Barney machine. When this bank polled their customers about Barney, can you guess what feature people liked most about him? It was his smile. I understand that some of you are getting a video at the same time. Let me see if we can pause that. I apologize for the confusion with the video. If there's a way for you to close it for yourself, please go ahead and do that. For those of you who are only hearing me, I'm going to pause here for a moment. And I'm going to keep going now. Tim, let me know if we're having more trouble, okay?
Okay, sounds good. It should have passed by now anyway, so you should be good. And when you go back,
Okay.
It should automatically play. Sorry for any confusion in the audience, and appreciate the feedback.
Yes, thanks everyone. Appreciate it. So, Barney. What was his most remarkable feature, the thing that people knew about him the most? It was his smile. Now, what I found most interesting about this was, first of all, Barney's not a person. And yes, I know you're looking at a white screen now. That's on purpose. The logo is just a collection of simple shapes and lines. But the most remarkable thing about Barney and seeing a smile on him is that he didn't actually have a smile. So what's going on here? Our memories are stored as the patterns we understand. When we store a pattern like face I trust, it can get attached to things like a smile. It's kind of like this drawing. In our minds, we don't have a clean separation between stairs and walking, or up and down, or trustworthy and smiling. They are related ideas, and they come to mind together. This is one of the strengths of our intellect, our ability to form and use patterns. However, these patterns also sometimes lead to errors in judgment, like remembering Barney's smile that's not really there. We call these errors cognitive biases. I'll give you another example. Primacy and recency are two other kinds of biases. When we see a list of unrelated items, we tend to remember the first item and the last one more than the rest. The entertainment industry knows this. When you watch credits for a TV show, you will see the first listed name is the biggest star, and the special guest stars are the last. They know that we remember the first and final names best. Now, because we're constantly making judgments and processing information, we are constantly at risk for cognitive biases. So what does this have to do with visual analysis? Well, our visual system is enormously influential in our brains. Data presented clearly reduces cognitive bias. And this is where the beautiful science of data viz comes in. Data viz takes advantage of how we perceive. It uses the power of perception in our brains to strip away the false patterns by focusing on what's right in front of us. We effectively hack our brains to work for us instead of against us. So how do we hack the brain? Science has started to teach us the specific ways we can draw shapes to create meaning visually. Here are some of these ways to draw. We've seen some of them at play already, like color, hue, and size, but as you can see, there are many more. These visual features activate the powerful visual system in an incredibly fast way, usually before we can even begin to think about it. So, to help explain how fast this perception happens, I'm going to go back and play that video again now. For those of you who have seen it already, it is as fascinating as it was the first time, but the thing I want to call out is notice, as you follow along with the video, how quickly you can pull out the colors and shapes that you're being prompted to see.
This video will demonstrate a number of pre-attended features, tasks, and visual interference which can occur in the low-level human visual system. To begin, consider a simple target detection task. Try to determine whether a target red circle is present or absent in a sea of blue circles. Apart from viewers who are red-blue colorblind, the target is easily identified as present or absent in each display. Notice that increasing the number of elements and decreasing exposure duration does not make identification more difficult. Pre-attentive tasks are rapid, accurate, and independent of display size. Other visual features are also pre-attentive. For example, shape or curvature. Try searching for a red circle in a sea of red squares. Experiments have shown that this task is also pre-attentive. These results might suggest we can display two attributes simultaneously, one with color, the other with shape. Try finding a red circle in a combined background of blue circles and red squares. Put simply, this search is very difficult. Targets with no unique visual feature form a conjunction. Users must scan serially through the display searching for the target. This task is not pre-attentive and shows exactly the kind of visual interference we would like to avoid. Other tasks are also pre-attentive. For example, boundary identification. Try to determine if the hue boundary is horizontal or vertical. Notice that some displays used a constant shape, while others varied the shape randomly across the array. This has no effect on our ability to identify the hue boundary. Let's reverse the data feature mapping and try to identify a boundary formed by a difference in shape. Shape boundaries displayed with constant color are easy to detect. A random color pattern, however, masks the shape boundary. This type of visual interference is known as feature hierarchy. For this task, the visual system favors color over shape.
You're good to go, Jeff. It stopped.
Great. Thanks, Tim. So you got a sense watching that video how powerful visual features can be. Let's talk about how to use them for visual analysis now. To start, let's think about the kinds of data we have. Well, there are three basic kinds of data. First, there's categorical. That's how we break the world down into groups. The groups can be as large as continents or as small as individuals. Then there are ordinal values. These are simply categories that can be put into a meaningful order, and dates sometimes can be ordinal as well. Finally, there's quantitative data. These are the measurements of the world around us. They're values that can be placed on an axis, or things that we can find the difference or distance between. So, what are the best visual ways to communicate these different data types? Well, for categorical data, we can communicate it by position. This is pretty simple. If you think about a spreadsheet, each row is a different position representing a category. Color hues. We've talked about that a little bit as well, how color can differentiate things. One thing is red, something else is green, something else is purple. Shape can divide things into categories as well. A square has a different meaning than a circle, and so forth. Clustering and boundaries, we saw a little bit of that in the video as well. The way things were arranged on the screen broke things apart into categories. Ordinal data also can be arranged positionally. Think of how confusing it would be if you had something like small, medium, and large, but they were presented in a different order in data. It wouldn't make much sense if it went small, large, medium. Size as well, you can imagine, maps very well to ordinal values. Color intensity, the more of a color there is, the more of a value there is. Color hues, you have silver, gold, bronze. And shapes, again, can be used for ordinal values. And finally, looking at quantitative values, again, Position rises to the top of the list. It is the single strongest way that our brains can organize information. Building on position, we have values like length and size. So length would be the length of a bar. Size would be how big something is. Color intensity. To communicate, again, quantitative values that are larger, colors are more intense. And I can use up to 2 color hues this way as well. So more positive values are blue, more negative values are orange, for example. And then finally, one more is orientation, which is great for communicating change. This is why line graphs are so powerful at communicating change over time, because we are super fast at perceiving whether a line is angled up or angled down. So having looked at the way we can communicate data, let's go back and see what science tells us about Minard's drawing. He uses position to communicate where battles happened, for sure, but you can also see vertical position in the line graph representing temperature. Color hues dictate the direction of travel. Size communicates troop strength. Orientation indicates direction of travel and whether the temperature was rising or falling. Let's take a look at some other time-tested examples of data visualization and see how modern perceptual science explains why they work so well. In the 1800s, a London doctor named John Snow used this map to show how cholera was being transmitted by contaminated water from a pump here on Broad Street. The black marks like these here show the number of infections at an address. Like all maps, this one uses the visual feature of position to illustrate geography and its correlation to the disease. The length of the black marks maps to the quantitative value of the number of patients. And clustering shows us how the outbreak was centered around the contaminated well. This is another chart from England in the 1800s. This one was made by Florence Nightingale, and again, it's a rather grim story about death. She wanted to explain to Parliament, though, and government officials, how battle wounds, shown in red, were taking nowhere near as many lives as treatable conditions, which are the bluish-gray. She used position around the circle for the ordinal value of months, the size to represent the quantity of deaths, and color hue as the category of cause of death. And finally, one last example. This is from 1,300 years ago. These star charts are from the world's oldest complete preserved star atlas. Back before Europe was even a thing, Chinese astronomers used position to document the locations of the stars, clustering of shapes and lines to represent constellations, and color hues to represent the categories of 3 different schools of astronomy. So for over 1,000 years, we've been using our intuition to describe what we're seeing around us. Some of our most powerful successes have relied on perceptual psychology that we've only understood in the last few decades. So, let's bring together our ancient fascination with another recent scientific advance. 6 years ago, the Kepler Space Telescope was launched. I just want to pause and repeat that for a moment. This is a telescope in space. By getting a telescope up out of the atmosphere, you get a much clearer image. So clear, in fact, that you can watch a distant star over time, see the color or intensity change slightly every so often, and figure out that that is a planet changing the light that reaches the telescope. Earlier this year, astronomers announced Kepler had spotted 8 planets that might be hospitable to human life. So the data set here we're going to look at has one row for each planet we think we may have seen circling another star. Let's take a look. One moment while I get my screen share started. We're still here. Okay, so here we are. We're looking at this data in Tableau. First, let's see how many planets Kepler thinks it might have seen. So now I've got this big collection of blue dots. Each one of these blue dots represents one planet Kepler thinks it's seen. We can look at this and see, well, it's probably more than a few dozen and less than a few million. We get a rough sense of size pretty quickly. So out of all these potential planet candidates, which ones actually have turned out to be real data and which ones were just noise? Well, I'm going to take the disposition, which is the data, the name that scientists give this, and color the planets by this. And now we can see everything that's orange has been confirmed. There's been enough data about it that we know that that represents a planet somewhere orbiting another star. The blue ones are the ones that we've got some data, but we haven't confirmed one way or another. And the gray ones were the ones we've confirmed actually were just noise in the data. They weren't really there. So now we know a rough idea of how many there are and what's the proportion of the data that we found that's meaningful. So let's take a look at how these stars are arranged with respect to each other. Now, it turns out that stars, just like on the Earth we have latitude and longitude, you know where stars are in the sky by two values called right ascension and declination. I'm going to go ahead and start spreading these stars out by right ascension and declination. And just like a map, we don't need to include a 0 in this scatter plot. So here we go, and this is the shape of the stars that Kepler has been studying in the sky where it thinks it might have seen a planet. You see this and you may notice right away something jumps out. There's a shape to this, a very regular grid. When I discovered this, I got really curious about it. Where did this regular grid come from? Well, it turns out if you look inside the telescope, this is what the camera array looks like inside the telescope. So the shape of this data and the way it clusters with each other actually tells us something about the construction of the instrument used to look at it. So going back to this now, how much of the sky have we actually looked at? If we've been finding all these so-called exoplanets, where are they? Well, just like latitude and longitude, declination and right ascension can be used similarly. So I'm going to say for declination, let's look from minus 90 degrees to 90 degrees, from the South Pole to the North Pole. And right ascension wraps around the planet from 0 to 360 degrees. And now you can see that is the tiny part of the sky that we've just started to study with Kepler. So we found out that there are some planets we might be able to live on. Scientists look at this by looking at the size of the planet and how close it is to the sun and how hot its own sun and how hot it is. So if we want to look at a couple of measures with respect to each other, a scatter plot is a good way to do this. Again, we're using position now to look at the size of the planet, measured in number of Earths, and the orbit size of the planet, because if it's too close to the sun, it's too hot, and it's too far away, it's too cold. That's why these are called Goldilocks planets. Not too hot, not too cold, not too big, not too small. So let's get rid of some of these candidates that we've seen that no longer fit. So first of all, let's get rid of the planets that are too hot. Turns out that Earth is around 245 degrees Kelvin on average. So if we get everything that's above 275 degrees, that rapidly gets rid of a bunch of planets that are too hot. And if you look at planet radius, you can imagine that anything that's 5 times the size of Earth, like this one up here, is far too big for us to live on. We'd be crushed trying to just walk around. So if we reduce the planetary radius to something maybe closer to Earth's, like 1 3/4, now we can see 9 candidate planets. We've gone from hundreds down to just 9. And the ones that are the filled-in circles are the ones that actually the scientists have confirmed are potential places where humanity might be able to explore someday when we can go to other stars. So we use the power of visual analysis, the power of data visualization, to take this collection of data from a telescope in space, and we've used it to take a look at, to narrow that data down and find just the planets we might be able to travel to someday and find a new home. Of course, what makes this science so cool to me is that DataViz opens the funnel for how much information humanity can actually use. As a species, we have more information available than ever. We know where planets are in the sky. And you and I, are bringing the world a technology that lets us access that information meaningfully and purposefully. Of course, this is not a one-time activity. Data is constantly coming into being, changing and growing. Our interests and needs are changing and growing. So at Tableau, sometimes we draw that process, that cycle of inquiry like this. We call it the cycle of visual analysis. You notice it's not a linear conversation. It jumps around. It's more like a conversation than a flow of data through some process pipeline. It follows twists and turns as our understanding of the data grows. It's important that our tools stay out of the way of this conversation so it can proceed between people and their data. So just looking at the screenshot of Tableau again for the moment, you can see that we've tried to make it possible to get the tool out of the way as best you can. I talked about the power of position. And the columns and row shelves are what we use to scatter those stars out, spread them out to give them meaningful positional information. And so those are right at the top of the screen, so you know those are the most important ones. And then on the left side, you might see targets for color and size and label. Again, right there on top, we can take advantage of the power of visual perception to help us understand our data quickly and easily. So starting from this foundation of the user experience, there are 4 key aspects that we at Tableau think are crucial to a data conversation, regardless of what tool you use. First, a conversation is incremental, right? When we talk to each other, each sentence and idea builds on what came before it. So you want to be able to ask and answer questions of your data in this incremental way. As I ask one question, I get an answer. And the answer to my next question should just be a drag or two or some other simple operation away. A conversation among people is also expressive, and that's the second principle I want to talk about. A conversation with data should be expressive as well. You might be looking at something as mundane as the travel of consultants as shown in that map on the bottom right. And it's still important that you can shape that data in a way that you can connect to. Now, the expressiveness of data is no less important than the expressiveness of art, I would argue. Imagine if all creativity had to be channeled only through words or only through painting or music. Who could picture the Belarusian meat industry with whimsical icons and the title up there in the top left, Molchania Yanyat, Silence of the Lambs? Or that an entire season of a sports league's games could be painted like some abstract barcodes. Something as rich and expressive as the world's data needs an expressive palette to represent it. Now, a conversation also needs to get to the heart of its topic. And for data, that means you need to converse directly with the database. All the give and take of a data conversation, all the expressive views, all of this should work directly with the underlying data, not intermediated by queries and tables. It doesn't matter whether your data is in an immense server farm or a small text file. Tools should get out of the way and not try to force themselves into the middle of a discussion. People who understand the data should be the ones who can ask and answer the question. It's a unified experience. And finally, I haven't talked about this much today, but you want to have an interactive direct surface. And that's the 4th principle, directness. We're not just creating static data visualizations anymore that our users can see, but they should be live views that support things like tooltips and highlighting and filtering, ways to reach out and touch the data and ask it questions without even needing to know where the database is or how to build a database. So we're getting close to wrapping up. But before we do, I wanted to talk a little bit more about the history that got us here. Humanity has long used tools before having the science to explain why they work. We used fire, for example, and the wheel for millennia before we understood exothermic chemical reactions or the laws of physics. So let's step back in time before we studied visual features and the counting center in the brain. Over 500 years ago, white men from Europe arrived in the Marshall Islands in Micronesia in the middle of the Pacific Ocean. The Marshall Islands are miles apart from each other. Standing on the shore, all you can see is ocean. Yet the Marshallese navigators would climb into canoes and paddle without error from one island to another. They didn't use paper maps, compasses, sextants, or even the stars to guide their way. They would do it by day. To the white men, this was nothing short of magic. Over time, they learned from these navigators that when they were kneeling in the front of their canoes, they could see and feel the shape of the ocean. The interference patterns of the waves rocking the boat carried the secrets of the currents as they shifted through the islands and the way the water would reflect off the long submerged slopes of the island shores. So how did these navigators learn their techniques? Well, I'm sure they practiced, no doubt, but they also used data visualization. This display, which I got from the Museum of Science in Boston, shows a stick map. Built from coconut fiber and rocks or shells, this particular stick map is a teaching tool. It represents a fictitious set of water movement through a made-up set of islands. In other words, this is like a sample data set. So this curve here represents the current coming from the right. And there are 3 other curves representing more currents from other directions. These 4 rocks represent islands. Accomplished navigators used tools like this one to teach the principles of Marshallese navigation to their apprentices. A complete stick map might look like this. What's most interesting is that these complex data visualizations were often not actually shared among navigators. They were reference tools created by a navigator for personal use. My idea is that perhaps once someone created the first one of these, someone else noticed it, kind of sidled up next to them and said, "Hey, what's that you got there?" And a great idea started to spread from island to island. But now, today, you and I, we don't have just charts and graphs. We have the science behind them. We've started to unlock the principles of perception and cognition so we can apply them in new ways. When humanity unlocked the science behind fire and the wheel, we learned to harness chemistry and physics in new ways, and we revolutionized the world with steam engines, internal combustion vehicles. The surface of our planet literally changed, and how we communicate with each other shifted forever. Humanity is at the dawn of a new revolution now. And those of us using data visualization are putting the beautiful science into the hands of millions of users. And I'm excited to see where we all go together next. So thank you for your listening. Thank you for your attention. And I believe it's time now to start up some Q&A.
Thank you, Jeff. Great presentation. And thank you to our audience for bearing with us during that glitch with some double voice talking going at the same time. So far, we just have a few questions. So, Jeff, you did a really good job covering the topic, apparently. But I want to remind the audience to don't be shy. Go ahead and ask any questions you might have for Jeff along the way. And I'm going to move the slide forward to Jeff's contact information during the Q&A portion. Please feel free to take down his email address, and you can contact him following the webinar if you want to have a personal conversation with him following. So the first question, Jeff, is how do you define the quality of data visualization? And can you provide some details in terms of factors to determine what would be a good data visualization?
Sure. I think that that is an interesting question. The quality I would look at in a couple ways. First, you want to be able to focus on the data itself. Edward Tufte in his books famously calls it chart junk when you have a lot of unnecessary decoration around the data that you're actually trying to understand. It turns out there's actually a balance there because some amount of symbology, even if it seems decorative, can actually help create a more lasting impression. It's kind of interesting. But in general, get rid of as much noise around the data as you can so that the audience can focus on the data itself. And then the other is take a look at how you're using it. Going back to those pre-attentive features, the visual features of, I'm sorry, the ways of data, yeah, the pre-attentive features. Things like position and size and color and shape, these are all different ways to communicate information. Are you communicating the most important features with position? Are you using colors in a way that help communicate categories? Or are you using color intensity for ordinal or quantitative values? These kinds of practices are all the things that help make a single data view high quality. And finally, considering the world of interactive visualizations, how are you letting your users of this data, the people who are perusing it, actually ask and answer questions themselves? Again, some of those principles of directness with things like tooltips and being able to filter or highlight data interactively. Those are all important things to make a viz high quality.
Okay, very good. Thank you, Jeff. Next question is, what would you recommend as a good first stage visualization to investigate unknown data?
Yeah, that's a tricky one. So you've got a pile of data and you don't know what it is. Well, the hard part, of course, is that a high-quality data viz is one that does communicate something about the data. So I'll give you some ideas of some of the things that I initially do when starting to look at data. First, you want to get just a sense of two things, the size and the grain, or what I'm going to call it. Size is how much do you have? Are you dealing with hundreds of rows or millions of rows or billions? That'll help understand, does this data need to be aggregated or filtered in meaningful ways first? And next is, what's the grain of the data? How can you understand you need to understand what each row represents. For example, from looking at sales data, is each transaction in this database an entire sale representing a bunch of line items all rolled together? Or are all the line items split out? So I sold 3 rolls of tape and 5 pieces of paper and 4 pencils, and those are 3 different lines in one transaction. So those are a couple of sort of fundamental things. Getting into the visual part, how can you start using the categories and information you have to start understanding it? So you might want to look at the number of records you have over time to understand, is this something that's been growing over time or steady state, shrinking over time? Look at some of the categories where you understand what they actually are, especially if the number of entries in that category is the cardinality, as it were, was fairly small. So if I broke this whole set of data down into 20 groups and started aggregating something or averaging something, what can that tell me about the data? So start looking at the distribution information. A final way to do that is to look for relationships. This can be a little bit harder. And you can use a scatter plot to do that, where you take 2 quantitative values and you compare them to each other by spreading them out by some category. The tricky part about doing that with a scatter plot is until you find a meaningful categorical breakdown that actually does show some correlation, it is a little bit like spelunking through the data. So I'll pause there.
Very good. Very thoughtful and detailed answer. Thank you, Jeff. Next question is, how does Tableau help a novice user translate the underlying science to effective data visualization?
Sure, happy to answer a Tableau-specific question. Thanks for asking. So I think that what we've tried to do is to get back to that. Actually, I'm gonna flip the screen back to that screenshot of Tableau I showed before. So again, looking at just what we help people do in building a basic data viz, we try to arrange the controls on the screen in a way that promotes the best use of data viz. So rows and columns are those 2 drop targets across the top of the view that spread data out positionally. And it's a single drag and drop to encode things, as we call it, by color or size or shape. Tableau also does things like smart tooltips by default and turns on highlighting so as you interact with a legend by default. That helps understand the data in a much more interactive way. Translate the underlying science to effective data. I think those are the most important ways to look at the ways that the card system and the way you can drag and drop pills of data onto shelves. A bunch of Tableau words out in one sentence there, but I can drop my pills, which are the data, out onto the shelves and spread it out using the perceptual principles we've talked about. That's probably what Tableau does best to help the process.
Okay, sounds good. By the way, you're getting lots of accolades for a good presentation, Jeff. Just want to share that with you. One additional question is if you can provide some recommendations on best practices around data visualization for, in quote, data in motion versus, in quote, data at rest.
I'm not sure exactly what the question means, but I'm going to take a guess. It's something to do with live data versus static data. If you're actually talking about physical movement, go ahead and ask another question. We can get to that too. But so live data versus static data is an interesting one. If you have a screen that's actually animated, it adds a new layer of complexity onto the data visualization. Often I find that it's better not to have the data animated unless you have a very thoughtful way that it's providing meaningful information. I'll go with a very simple example because it's hard to know what domain we're talking about, but I'll go with just the dashboard of a car. If you consider the velocity you're going at, I get meaningful information by looking at the speedometer and whether it's moving up or down. And that's something I can quickly perceive because we're actually, another thing that our visual cortex is very good at is noticing motion out of the corner of your eye. Your periphery is very good at noticing movement. So if my speed is changing, I'll actually see that speedometer needle changing. Many cars nowadays have digital speed readouts where you actually see numbers instead of a moving needle. And that doesn't do as effective a job because it's sort of jittering around so much. I could just be moving a mile an hour slower or faster as minor variations in the road or whatever. And yet I still have the same amount of animation to which I need to attend. So I would say if you're looking at live data, it's important to think about what key one or two pieces out of the live data do you need to attend to, and how can you, with the minimum amount of movement, communicate that?
Okay, very good. This next question is a little bit tricky for me to read, but I'm going to do my best, so maybe you can make sense of it. So in your talk, one of the principles you talked about, Jeff, was dealing with data directly, and the audience member is asking if you are suggesting that they not implement data transformations via an ETL job and similar transformations. And they just want clarity. Is that what you're saying, to not implement data transformations via ETL? Because this person, in this case, many times they are working with clients who have data that is otherwise incomplete.
Sure. Yeah, no, it's not. I mean, in an ideal world, we wouldn't need ETL, right? The data would already all be cleaned up and just how we need it. But of course, that's not how data really shows up in the world. For anyone who doesn't know what ETL is, it stands for extract, transform, and load. I don't know why we still call it that, but I mean, I understand the process. But it basically means data cleanup, right? I've got a table, there are missing values, or there's a column in there, but it's coded to something that's not human readable. It's a bunch of digits or some character codes, and I want to turn that into something readable. Or it goes on and on, all the different ETL processes you can do. I've got 20 files that represent 20 months, but I want to look at them at the same time, so I want to union them together. No, ETL is actually a fundamental part of the data analysis process, and it's going to be forever. We're always going to be continually getting new data that's not necessarily connected cleanly to the data we already have. So I would say that the challenge for us as data scientists and people who do data visualization is how can we extend our interactivity into the ETL world? If I do create a data pipeline where I've got a 2-hour ingestion process where I've got to take my data and get it through this pipeline, if the data is always going to be a couple days old anyway, a 2-hour ingestion process probably isn't that big a deal. But it can break, it can be fragile. So how do we basically take the same principles of interactivity, and by which I mean things like incrementalness and expressiveness and directness, things that let me communicate directly with the data and bring those to ETL as well, so I can see where my data might be broken, so I can understand what kind of transforms I can apply to get it into shape for visual analysis. I would sort of rephrase the question and say, how can we take the tools of visual analytics and use them to improve the process of ETL? I hope that answers your question. It's a great question. I'm spending a lot of time at Tableau in the next couple of years actually continuing to build on a much more visual ETL process we've started to add to the tool. So,
very, very thoughtful answer again, Jeff. Thank you. Next question is, one targeted visualization better than having multiple visualizations at the same level? And if so, which one would you suggest is better?
The answer is a firm, it depends. I think that it depends on, like, so there's one sort of, I'm going to imagine that you have a case where you might be looking at one view that uses lots and lots of different kinds of encodings. So I've got two quantitative values spread out in two axes, and I've got some color representing something else, and I've got a shape representing something else, and maybe I've got some labels in there. That may be fine, depending on what the data is. Look at a map. A map is a really rich, complex encoding that uses lots and lots of different kinds of encoding all at the same time, and is often very meaningful. But multiple visualizations at the same level often afford more detail with less need to intellectually understand what I'm seeing. So, for example, if I were to take the same information, the same rich view, and split it into two related views, so that I could do something like filter my scatter plot by picking marks from a bar chart, or have some other way of quickly highlighting parts of the data based on what I see somewhere else in the data, that may also help build my understanding. It depends on the exact shape of the data. It depends on also how frequently you're going to be looking at this information. For example, let's go back to the mapping example and try to come up with something that I can describe over the phone. If you think of nautical charts, there's a lot of information put into nautical charts that don't necessarily make meaning to the person who's not a mariner. And when you come up with a really complex data viz with lots of extra annotations that are really interesting, it may be very helpful and powerful in exactly what the audience needs if that's the information they're expecting. That's why I say it depends. It really depends on the audience, kind of information they're used to seeing, and what they want to see at any given time. Kind of a wishy-washy answer, but I hope it helps.
No, I think you answered that very well. Next question is, Jeff, can you provide some information in terms of the major differences in Tableau versus sort of Excel functionality?
Sure. I think they are two complementary tools. There's no reason why I would say you need one and not the other. So Excel is great at looking at tabular data and to be able to arrange that data and do sort of a point-level ad hoc analysis. If you want to be able, so a table, in general, just to back away from Tableau and Excel in specific, but in general, a table is great when what you need is a specific answer. If I've got, for example, 4 cities and 4 quarters and a 16-cell table that shows me the sales for each of those cities in each of those 4 quarters, and I want to know, what was sold in Wichita in the second quarter, that's exactly the information I want. Now, if I want to know which city grew the fastest over those 4 quarters in terms of sales, now I want to be able to do things like compare slopes of lines, is how I do it visually. So different tools are going to be better at answering different questions. I think once you get into trying to look at anything more than a couple numbers at a time, you want to move to a more visual tool like Tableau. This also relates to that ETL question that came up earlier. Often, even here at Tableau, we end up using Excel to do some amount of ETL, to look through the data, to understand the shape of it, and to try to clean it up. Ideally, I would like us to better support those kinds of things in Tableau more, because that kind of visual analysis, even a simple thing like how many null values are there in this column, it would be great to see that as a visual that shows me the proportions instead of making me do that math to understand it. So, and I'm going to pause there because I think we're just about out of time.
Yeah, we're just about out of time, but there's a couple questions have come in about sort of additional resources in learning data visualization. If you can just provide a quick answer to other resources or books that would be helpful to those that are sort of early in the stage of learning data viz, that would be great.
Yeah, I'll throw out 2. One is Visualizing Information by Edward Tufte. It's a seminal work, well, not seminal, classic work, I'll say. And another one is Show Me the Numbers by Stephen Few. Tufte is much more about static data viz and focusing on the data over the labeling around it. And Stephen Few gets very down to the heart of much more like modern interactive data visualization, and does a wonderful job about talking about things like building interactive dashboards and building views yourself. I think anyone reading both those works would profit enormously. Very
good. Thanks, Jeff. So this brings our webinar to sort of the close. I just want to make a couple of quick announcements to everybody. To please mark your calendars for May 26th and our next Data Science Central webinar, 7 Reasons to Combine SPSS Statistics and R, which is sponsored by IBM. Also, as I mentioned earlier, this webinar has been taped and will be made available later on this afternoon at datasciencecentral.com. I just want to thank Tableau for their sponsorship and Jeff for such a great presentation and very good, thoughtful answers to some very good questions. It's been a pleasure being your host for today's webinar, and I look forward to seeing you all on May 26th again. Good day.